be defined as the capability of an airplane to operate effectively while serving a specific purpose. Among the elements of performance are takeoff and landing distances, rate of climb, ceiling, speed, maneuverability, stability, payload, and fuel economy. Some of the elements of performance may be mutually exclusive. For example, high speed versus short landing distance, long range and high payloads, or high rate of climb and fuel economy. Airplanes are designed with specific performance goals, which explains the design differences among various types of airplanes.
Consider the high payload, low speed, short takeoff and landing distance of the airplane used for agricultural spraying. Compare that airplane to the sleek, high cruise speed, relatively long takeoff and landing distance of the turbojet airplane. The density of the atmosphere, which is its weight per volume, has a direct bearing on airplane performance. Airplanes perform better when the atmosphere is dense. Airplane performance is degraded when the atmosphere is less dense.
Pressure, temperature, and humidity affect the density of the atmosphere. The atmosphere is more dense when pressure is high and both temperature and humidity are low. Low pressure, high temperature, and high humidity make the atmosphere less dense.
Density altitude is pressure altitude corrected for non-standard temperature. Regardless of the true altitude, an airplane's performance depends on the existing density altitude. If pressure altitude and temperature are known, density altitude can be determined by either using a density altitude chart or an E6B. Recall that pressure altitude is indicated altitude corrected for non-standard pressure. If an altimeter is available, simply set the barometric scale to 29.92 inches of mercury and read the pressure altitude. Without an altimeter, the indicated altitude and altimeter setting must be known. Printed next to the density altitude chart is a table to convert indicated altitude to pressure altitude. If the altimeter setting is 30.30, subtract 348 feet from the indicated altitude to obtain pressure altitude. If the altimeter setting is 28.22, you must interpolate to find the correction or conversion factor. The difference between altimeter settings of 28.20 and 28.30 is 97 feet, or 9.7 feet for each hundredth of an inch. For 28.20, add 1,630 feet to the indicated altitude. 28.22 is 2 hundredths more than 28.20, so the feet to be added should be decreased by 2 times 9.7, or 19.4 feet, for a total correction of 1,610.6 feet to obtain pressure altitude. On the density altitude chart, the width of a pencil line is 50 or more feet. Taking the closest listed value has a maximum error of less than 50 feet. However, interpolation may be required for questions on the written test. Before trying to use a performance chart or table for the first time, take a minute or so to acquaint yourself with the graph or table. The density altitude chart has temperature on the horizontal axis. Note the temperatures are on both the Fahrenheit and Celsius scales. The vertical axis of the graph is labeled density altitude. Close to the top of the chart, the lines which slope up from left to right are labeled pressure altitude. Some density altitude graphs have a line which slopes down from left to right, labeled standard temperature. To find the density altitude for a pressure altitude of 3,500 feet and a temperature of 95 degrees Fahrenheit, enter the chart at 95 degrees and go straight up to a point halfway between the 3,000 and 4,000 foot upsloping lines. From that point, go straight across to read the density altitude of 6,500 feet on the vertical scale of the chart. The standard temperature line can be used to find the standard temperature at various altitudes. Standard temperature at sea level is 15 degrees Celsius, and the standard lapse rate is about 2 degrees Celsius per 1,000 feet. From the intersection of 5,500 feet pressure altitude and standard temperature, drop straight down to the temperature scale to read 4 degrees Celsius. With a 2 degrees lapse rate, temperature at 5,500 feet should be 11 degrees colder than the 15 degrees Celsius at sea level. Conversion between Fahrenheit and Celsius can be made using the temperature scale. 50 degrees Fahrenheit converts to 10 degrees Celsius. Electronic aviation calculators have a density-altitude function that requires pressure-altitude input. This calculator converts indicated altitude to pressure altitude as part of the density-altitude function. To find the density altitude for an indicated altitude of 3,612 feet with an altimeter setting of 30.04 and the temperature of 95 degrees, first select the p-dalt function. Respond to the indicated altitude prompt by entering 3,612 feet. Then enter the altimeter setting to respond to the baro prompt. The temperature prompt calls for temperature in Celsius. Enter 95 degrees and use the convert function to convert the Fahrenheit temperature to 35 degrees Celsius. After entering the temperature, the calculator shows pressure altitude of 3,500 feet and density altitude of 6,500 feet.
In this section, we'll be looking at numerous graphs and tables, but remember, they are for illustration only. For actual flight planning, you'll need to use the charts and tables specifically developed for the airplane you are flying. Performance data for a specific make and model airplane are in the Pilot's Operating Handbook.
Depending on the manufacturer, the data may be in tabular form, graphs, or a combination of tables and charts. Rather than looking at each individual chart or table, let's look at representative examples of each and deal with the fundamental concepts to use them. This is a stall speed versus weight, flap setting, and angle of bank chart. The left-hand section is used for the weight of the airplane. The dot-dash lines are for calibrated airspeed at the stall, with the solid lines for indicated airspeed at the stall. There are downsloping lines for 0 and 40 degrees of flaps. The right side of the chart accounts for the bank angle. All other conditions being equal, the stalling speed is lower when the flaps are extended 40 degrees. With all other conditions being equal, increasing the weight or bank angle results in a higher stall speed. Some pilots call this type of chart a chase-around chart. You do indeed chase around the chart, but within and along the guidelines on the chart. Virtually all charts have a sample problem and the path of the solution for the problem. The solution path for the sample can be paralleled with the data for another set of conditions. What is the indicated stalling airspeed at 2,325 pounds weight and 0 degrees of flaps in a 30-degree bank? Starting at the maximum weight line, go up to the 0-degree flap curve. At maximum weight of 2,325 pounds, the solid line for indicated airspeed and 0 degrees flaps, and the dot-dash line for calibrated stall speed at 40 degrees flaps coincide. From that point, go straight over to the 0-degree bank angle. To reach 30 degrees of bank, guide on the curving lines which slope up. Stop at 30 degrees of bank and go straight across to read 54 knots as the indicated stalling airspeed. Another manufacturer presents stall speed information in tabular form. While tabular information appears easier to use, it does have the disadvantage of being limited to specific conditions. Any variables which do not conform to the table must be interpolated, but in some cases cannot be interpolated. As an example, the relationship between stall speed and angle of bank is not direct, and the tabular data cannot be interpolated. Stall speeds are listed for most rearward and most forward center of gravity. Recall that the forward CG causes a higher stalling speed. With all conditions equal, this airplane has a most forward CG stalling speed more than 10% higher than that for the most rearward CG stalling speed. At a weight of 1,670 pounds and 0 degrees bank, the indicated stalling airspeed with the most rearward CG is 36 knots compared to 40 knots at the most forward CG. Takeoff and landing distances are affected by several variables, including density altitude, airplane weight, runway slope, runway condition, and wind. If the wind direction is at an angle to the runway, the amount of the headwind must be determined using either a graph or aviation calculator. Let's take a look at the wind component graph. There are angular lines which represent the difference between the wind and the runway. Arcs represent the speed of the wind. Headwind component is on the side, and crosswind component is on the bottom of the graph. Assume a takeoff on runway 36 with the wind from 320 degrees at 20 knots. What is the headwind component? The angle between wind direction and runway is the difference between 320 degrees and 360 degrees, or 40 degrees. Track the 40-degree angle line until reaching the 20-knot arc. Go straight across to read a headwind component slightly more than 15 knots. Track straight down from the intersection of the 40-degree line and 20 knots to read that the crosswind is about 13 knots. Takeoff and landing performance is usually broken down into ground roll required and total distance to clear an obstruction. Obstruction height is arbitrarily chosen to be 50 feet above the runway. Ground roll represents the runway required. Total distance is the ground roll plus the air distance needed to clear the 50-foot obstacle. This graph is for the total distance from brake release to clear the 50-foot obstacle. It's important to know the conditions for which the graph is valid. This graph is for takeoff from a level, paved runway with full power before brake release and 0-degree flap setting. As usual, there is an example problem with the path of the solution. The left portion of the graph is devoted to temperature and pressure altitude considerations, in other words, density altitude. Notice that higher pressure altitudes and higher temperatures cause the beginning of the plot to start higher. Starting higher in this section means the plot will end higher on the distance required scale on the right side. Weight considerations are in the center. The guidelines slope down as weight is decreased, resulting in the plot ending lower on the distance scale. In the wind section, a headwind allows the plot to move down, reducing the distance required. A tailwind makes the plot move up, increasing the total distance. Temperature is 18 degrees Celsius. Pressure altitude is 3,000 feet. Weight is 2,325 pounds, and the wind is calm. What is the total distance required from brake release to clear a 50-foot obstacle? Before plotting a variable, check the scale. Each small square on the temperature scale has a value of 2 degrees Celsius. From the intersection of 18 degrees and 3,000 feet, go straight across to the beginning of the weight portion of the graph. The airplane is at maximum weight, and the distance required cannot be shortened. Go straight across to the wind portion. The wind is calm, which also doesn't shorten the distance required. The plot then goes straight through the wind portion. Each small square on the takeoff distance scale is 50 feet, for a total distance of 2,800 feet. Now, let's use the same pressure altitude and temperature with a weight of 2,000 pounds and 10 knots of headwind. This time, when we reach the weight portion, we'll follow the guidelines down to reach the 2,000-pound weight, which reduces the distance needed. From the point where the 2,000-pound weight is reached, go straight across to the zero wind line. From the zero wind line, follow the guidelines down to 10 knots and straight across to the distance required scale. Read the takeoff distance of 1,650 feet. To make good the takeoff distance of 1,650 feet requires a specific indicated airspeed for liftoff as well as climb. To find these speeds, go back to the weight portion. At the 2,000-pound weight, read the liftoff indicated airspeed as 45.5 and the indicated airspeed over the barrier or obstacle as 50 knots.
Using a chase-around graph is easy, as long as you remember to enter at the proper point and follow the guidelines up or down to reach the variables involved. Other graphs may have a different configuration, but the procedure is the same. Plot a point and go on to the next variable.
This landing distance chart is valid for a weight of 2,325 pounds, power off, flaps 40 degrees, paved, level, dry runway, maximum braking, approach speed 63 knots indicated, and full stall touchdown. While the pressure, altitude, and temperature section is familiar, the wind effect on landing distance is presented differently. In both the ground roll and total landing distance sections, a dot dash line represents 15 knots of headwind, a solid line, no wind, and a dashed line, 5 knots of tailwind. Wind speeds other than those lines can be plotted by spacing between the lines. In the ground roll section, there are 8 small squares between no wind and 15 knots of wind. Each small square has a value of about 2 knots. A 4-knot headwind would be plotted 2 squares to the left of the calm wind line. Let's plot the landing distance for the same airport with the wind conditions we used for the takeoff graph. From the intersection of 18 degrees and 3,000 feet across to the ground roll section at 10 knots places the plot 2 small squares to the left of 600 feet of ground roll. Each small square on the distance scale is worth 20 feet, which makes the ground roll 40 feet less than 600 feet or 560 feet. The 10-knot wind plot is 2 small squares to the right of 1,000 feet, making the total distance to land over a 50-foot barrier 1,040 feet. Takeoff at a weight of 2,000 pounds required 1,650 feet to clear the same 50-foot barrier, which only required 1,040 feet to land over. Before attempting to land at a short strip, check the distance required for takeoff from that strip. For virtually all airplanes, the distance needed for takeoff is longer than the distance to land. The Skyhawk POH presents this data in tabular form. Pressure altitudes are listed on the left side of the table, and temperatures are across the top. This takeoff distance table is for a short field takeoff with the flaps set at 10 degrees, full throttle prior to brake release, paved, level, dry runway, and 0 wind. Additional notes deal with procedures such as short field technique and leaning the mixture prior to takeoff from fields 3,000 feet or higher. There are also adjustments for wind and operating from a dry grass runway. If these adjustments are necessary, they must be applied in sequence and cumulatively. At a pressure altitude of 3,000 feet and 20 degrees Celsius, with a 10-knot headwind and a level paved runway, what is the distance to clear a 50-foot obstacle? At the intersection of 3,000 feet pressure altitude and total to clear a 50-foot obstacle in the 20 degrees Celsius block, the distance is 2,360 feet. According to Note 3, this should be decreased by 10% for each 9 knots of headwind. 10 knots of headwind calls for an 11% reduction to a total distance of 2,100 feet. If the variables don't fit the table, you can interpolate. After interpolation, the total distance to clear a 50-foot obstruction when the pressure altitude is 2,100 feet and the temperature is 11 degrees Celsius is 2,007 feet. This is only 353 feet less than using the next higher increments of 3,000 feet and 20 degrees temperature. Another trick is to find the average of the distances within which the temperature and altitude will fall. This yields the distance for 2,500 feet pressure altitude and 15 degrees Celsius. Doing this results in a distance of 2,160 feet, which is only 153 feet more than the interpolated distance. 153 feet is about how far the Skyhawk flies in 1 second. If the conditions of the day make it necessary to calculate the takeoff distance that precisely, wisdom suggests waiting for more favorable conditions of wind, temperature, and pressure.
We've looked at the different ways performance data is provided in the Pilot's Operating Handbook. Learn to use the data for the airplane you fly. Know the performance limitations for that airplane. It may not be necessary to check takeoff distance when taking off from 8,000 feet of runway on an airport near sea level on a cool day. Keep conditions such as temperatures, altitude, and runway lengths in the back of your mind. Know those that are close to the edge of your airplane's abilities. Establish a conservative envelope for operating the airplane. If any conditions approach the boundary of the normal operating envelope, carefully check and recheck the performance data. Finally, consider the variables that are not factored into performance. Let's take the first one, pilot ability. Ask yourself, can I consistently touch down on the spot I pick when I'm landing on a normal length runway? If you can't, there's no reason to believe that you'll be able to do so when the runway length is critical. In fact, the stress and tension of the critical length runway will probably further degrade your ability to hit the spot. Other variables are the condition of the airplane. Is the airplane dirty? Is the belly full of mud and debris? Is the engine still good but a little tired? Unfortunately, there is no table or graph to account for these variables. As a pilot, you must make important decisions. Old pilots have a record of erring on the conservative side of decisions. That's how they got to be old pilots.